Hello guys, we're Group 12 from Section 15. Our project is about the water dispenser that can dispense water in three temperatures. In next slide, we'll explain how our project works. As you can see, this is our block diagram. It consists of four inputs and two outputs. Four inputs are water supply sensor and water dispense button. And we have two temperature switches. And then the output is hot water outlet and cold water outlet. To make water come out of the system, A and B must be chosen all the time. For A is to make sure that there's water in the system, and B is just a push button so that the water will come out. So both must be high all the time. Okay, the logic behind our simulation is like this. So you have right now you have water in your system, and you push the button. So that's why both A and B are one. So for water temperature, choose you can either choose both or you don't need to choose both. So in both cases where you don't choose both or you choose both, so both the outlet will supply water, both hot and cold water, and then they will combine in the tap, and then finally you will have room temperature water. If you only choose hot water, in this case where C is only on, you will have hot water at the outlet. If you only choose cold water, in which case D is only on, you will have cold water at the outlet. So this is our truth table. As you can see, a large portion of our truth table output is just zero because when you look at it clearly, all the A and B are zero. So once again, A is for water supply check and B is for dispense button. Since if there is no dispense button push or no hot water, we will have zero in both outlets. So as you can see here, if the both water supply check and push button is pushed, we will see that there will be water output either on both inlets or one of the inlets.
Next, we will show you a quick video on how we design and simulate the circuit.
As you can see from the truth table, and we have to create two kmax for simplification because we have two variables. So the first one is for E and the second one is for F. So from the final equation, we drew the equation inside the quartus. For E, the final equation is A, B, and C plus D bar. So as we can see here, so for A and AB, we got A and B first going to an AND gate, and C and D bar, C plus D bar go to an OR gate, and then from that OR gate we go to another AND gate to get the output E. For F, the final equation is AB C bar plus C, AB into C bar plus C. So it's not very much different from E, but the only difference is the negation of C and D. So since AB already also present in E, we won't be drawing another AND gate. We will just use the AND gate from the first equation, as you can see here. We use only one AND gate for both equations, and then we for C and zebra, you can see we have to create another OR gate in the bottom. So yeah, the output of the OR gate and the very first AND gate goes into F. To change the design from using basic gates to universal logic gates, we derive a new equation by using De Morgan's theorem. So this is our comparison of the previous version and the new version. So in both designs, the amount of logic gates hasn't changed yet. Both remain 7. And then in this configuration, all the NOT gates are changed into NOR gate configurations. The previous AND gate between A and B has been replaced by an NAND gate as per the equation. As you can see here, the whole circuit changed because we just changed the final gates with the De Morgan equivalent. So actually, mathematically, the whole thing hasn't changed. It's just the use of logic gates have changed. Here is our functional waveform simulation. As you can see, for the first step, we group together all the inputs into one group so that the computer can automatically increment the binary value. As you can see on the right, the computer automatically increments the binary value per 10 nanosecond. So every 10 nanosecond, there is a change in binary value. As you can see, this is our simulation output. A is the MSB bit and D is the LSB bit. So as you can see, all both E and F are low for all the inputs in which both A and B are not high. So in this case, as you can see, all the inputs of A and B are high. You can see that the diagram in this picture starts from 1, 1, which means both A and B are high. As you can see, both A and B are high, and you can see that there is water output. No matter what, you can see that either E and F or both are high. So if only C is high, which means hot water is going out, hot water is chosen, you can see only E is high. When only D is high, you can see the only cold water is chosen, you can see the F is high. But in in cases when both C and D is chosen or not chosen, like 1100 or 1111, you can see that both E and F are high. So this is the end of our video. Thank you very much for watching.